Okay, cool. So this talk will be about optimizing model serving, inference on Kubernetes with model weight streaming. So I'm Ronen Dar. Happy to be here. I'm from the Run AI team. I was the co-founder and CTO of Run AI. We started in 2018. Run AI, we're doing what we call AI infrastructure orchestration. Run AI was acquired by NVIDIA last year, and now we're part of the NVIDIA team. Before that, I did my PhD and postdoc in information theory. And Ekin is here with me.
Yes, so I am the developer advocate from the Run AI team, now NVIDIA. I also did my master's in robotics cognition intelligence in Munich. So today we are going to talk about model inference.
Yes, so model inference, and we got this Run AI model weight streamer. It's an open source project that we published last year, and this is the work of Noah and Omer, who couldn't be here, but we're presenting their work. So great work by them. So let's start. So inference in theory, right? There is a training data set, and a model is being trained on that data set. It's being evaluated after the training, and if results are good, then it moves to inference, right? And inference, new data or users' queries are getting into the model, being processed, and new predictions or outputs are being generated, right? And this is what's the topic of this talk, right? About inference, how models can serve new requests in a cloud-native space on GPUs. So in traditional applications, with web applications, a common practice is to use autoscalers, right? There are users' queries getting in, and there are instances, replicas of applications running on in a container or on a CPU. And when traffic goes up, new replicas are spawned up, right, to serve those requests. And when traffic goes down, those replicas are being spawned down, right, to save costs. So that's with traditional applications, but with AI, it's much, much more difficult because of a few reasons. But one of the biggest reasons is the cold start problem, what we call the cold start problem. It takes a long time to spin up a new replica. Right, so first of all, the process of spinning up a new replica, it involves provisioning a new machine, right? But with GPU machines, it takes longer than provisioning a CPU machine, usually because there are less GPUs out there in the cloud, and because there are software libraries like CUDA drivers and CUDA kernels and libraries that wait a lot, and it takes time to install them. Second thing is the container image. Just loading the container image, usually in AI, those images are big. It involves a lot of Python libraries. Booting up the inference engine usually also takes not a considerable time. But this talk is going to be about the last part, about loading the model weights, right? Just downloading the model weights from a storage location into the GPU. And it can take a long time, right? It can be really significant. For example, with Llama 3, 8 billion parameters, usually it's being deployed with 16 bits per weight, and then the weights are around 15 gigabytes. So that's a lot, right? Llama 3 with 70 billion parameters, it will be more than 100 gigabytes, just the weights themselves to download from a storage and load into a GPU. DeepSeek R1, right, more than 1 terabyte. So that's huge. That's huge, and it can take many minutes. It can take sometimes more than 10 minutes just to download the weights and load into the GPU. So our goal is to accelerate that process. And why is it that important? Just a few slides about that. So a few use cases for inference. One is real-time inference, where there is one model and a high load, right? Many users querying just one model. And maybe there are multiple replicas running on a GPU. And as we said, right, we want to scale up replicas when traffic goes up and scale them down. Right? Usually those GPUs will be available. It's like a whole story of like provisioning new GPUs or not. Sometimes it's not possible to spin down GPUs, but let's assume that those GPUs are out there, and and if they are not used to run those replicas, they are used for some other workloads. But spinning up and down those replicas can take a long time, and users won't wait for a few minutes until their queries are being answered. So what we see usually happening is over-provisioning. Those GPUs are being, more GPUs are being provisioned to run those servers, and it means high costs and low GPU utilization. Another use case, it's code models, or like multiple models that needs to be served to different users, but infrequent load, right? Just infrequently, users are accessing one of those models. So what you will want to do, right, to scale to zero. Use scale to zero and put all of those models in some storage and spin a replica up when users are querying that model. But if that spinning up that replica takes many minutes, then you won't be able to do that if your application needs like low latency. So usually what we see is code models just being provisioned on many GPUs just to keep them warm, so latency will be low. And that's, again, high cost, low GPU utilization. Last use case for inference, offline inference, right? Running a batch job that process a lot of data in a batch fashion, right? So a job starts, it starts to process the data, outputs out there, and when the job finishes, those replicas are spawned down. But you're paying for the time that it takes to spin up those replicas, right? You're paying for those GPUs, and it can, if it lasts for several minutes, then it can be significant. So reducing that cold start problem, reducing the time that it takes to load models into your GPU can be significant, and that's the goal of this project. And Ekin will explain more about model loading and what we did with the Run AI streamer.
Yes, let's zoom into those containers and the model loading process a bit. So we have a storage that can be a local storage, that can be an object storage, doesn't matter. You have your model there. And first of all, you need to move your model to your CPU memory. And in the CPU memory, there are also some different things that might be happening, like sharding the model, quantization, etc., that will add up on time as well. And then after you load the model to the CPU memory, you need to transfer to those weights to the GPU memory, which is the second step. So these steps are happening sequentially. There is no parallelization, and it takes a lot of time. So when we started checking out the problem, we realized that we needed some specific things before creating the project. So first of all, the sequential loading will not work for us. So we need something that's working in a parallel manner. Second of all, we need a library that supports multiple storage types. For example, for safe tensors loader, S3 is not supported, and you might need to change your either storage or your code base in order to make your storage type work. So that's something that we wanted to avoid. Third, we want to be able to be compatible with safe tensors. Safe tensors format for model weights is becoming the state of art, and it's very safe. So we wanted to work with safe tensors specifically. And we want this project to be integrated easily with different inference engines. We don't want to keep pushing a single inference engine that you should use in order to leverage the project itself. So this brought us to Run AI model streamer. So we created this Python SDK with a C++ implementation, and we designed it in a way that it accelerates the model loading times onto GPUs from various types of storage, network file systems, S3, disk, doesn't matter. So the two key things that we are doing here is reading tensors concurrently from the storage while transferring them to GPU. And we also divide the tensors into equal parts for saturating the bandwidth while reading, because we want to saturate storage bandwidth with our loader. a bit more information about what is so special about Run AI Model Streamer. So as I said, we have concurrency. So we use multiple reading requests to read model tensors concurrently from storage, and we stream those to the GPU at the same time. We have some adjustable parameters, so you can adjust the level of concurrency depending on your storage type. You can choose how you want to divide the safe tensors, like the data chunk size for each thread. And you can also define CPU memory usage. For example, you might have a limited CPU memory, or you might have a gigantic CPU memory that you want to leverage. You can basically adjust those parameters with Run AI Model Streamer, and we will use that. Balanced workload for reading, that's super important. Tensors in AI come in different sizes. So we divide those tensors into equal parts for reading so that we can separate the storage bandwidth. We support multiple storage types, local file systems, cloud-based object storage. We support both. You don't need to convert any tensors from safe tensors and then other way around. So we support widely adopted safe tensors format. No need to convert them and store them separately. And we created the Run AI Model Streamer in a way that it is actually a safe tensors iterator. So it's very similar how safe tensors iterator, the traditional version of loading models, works. So you can easily integrate it with inference engines such as VLLM, TGI, etc., whatever you are using. And speaking of VLLM, if you are using a version that's higher than 0.66, we are also coming out of the box now with in the VLLM containers and VLLM versions, so you can try it out with VLLM as well. And now I want to talk a bit about our benchmarkings, like how does it actually perform in practice, right? So I will not go through the whole software stack. I will leave the QR code here later on so that you can read the benchmarking white paper. But we essentially used a meta model, MetaLlama 8 billion. It was 15 gigs, and we stored it in a single safe tensors file. As hardware, we used a single GPU, A10G, on AWS. And we chose 3 different storage types here. First of all, local SSDs. One is GP3 SSD, and the other one is IO2 SSD. The important thing that you should know about these two is IO2 SSD has a higher throughput. And we used Amazon S3, which is located in the same region with our instance. A little sneak peek to the whole benchmarking experiment you can see here, and QR code is here. Feel free to scan it to check out the whole benchmarking study. So the 2 main things that we checked is standalone loaders, safe tensors loader, Run AI Model Streamer, and Tensorizer, how long it takes for them to load a model from storage to GPU. And then we also checked how much time it takes to boot the engine and load the model with VLLM. So these are the 2 things that we checked out. And as you can see, we see quite some amount improvements with Run AI Model Streamer. And I want to share the key takeaways right now with you that we learned throughout these experiments. So first of all, concurrency drives speed up to a point. So concurrency is amazing. We checked out also different levels of concurrency from different storage types. And we see a lot of improvement when we increase the concurrency. But when you saturate your storage bandwidth, you are not gonna get more improvement because laws of physics, you can't do more. So we realized that we are hitting the limit after increasing concurrency enough. The second key takeaway is, as I said, balanced workload distribution is crucial. Tensors vary in size. Partitioning work into equal chunks among those threads help optimizing bandwidth saturation and making the streamer process faster. Because imagine like one tensor being gigabytes and one is megabytes, so then we need to wait for the reading process that's happening with the gigabytes of tensors first. And the third one is storage bandwidth. It matters a lot. So for deployments that you're gonna go for, if they demand fast model access, think about investing in high performance storage because we realize that it matters a lot, the bandwidth itself, if you're dealing with cold start problem. It reduces the load times a lot, especially in on-prem and hybrid environments. And as we talked before, Streamer has some parameters, so you should actually check out the concurrency, like the optimal amount of concurrency that you need specifically for your storage type, and also if you have any specific requirements for CPU memory, etc., you should tune the Streamer's parameters because it affects the cold start times quite a lot. And with S3, we got very good results. This is because our approach with S3. So creating an AWS S3 client per thread, with each thread sending multiple asynchronous requests to the backend, affects the performance quite a lot. It's super powerful. We see results that's under 5 seconds. I actually had difficulties to put them in the chart in the earlier days. So this was quite amazing. If you are using S3, give it a go. And some things that we noticed in the cloud, which is a bit independent of Run AI Streamer. So we were checking out the theoretical throughput that we are going to get, storage bandwidth we are going to get with the SSDs. Even if it's written 4 gigs per second in the documentation on the websites, we could only see up to 2 gigs per second. So keep in mind that there might be some practical limits that needs a bit planning. And also, if you want to run your own benchmarking with the Streamer or with something else, make sure that you are accounting for S3 caching effects. That's something that we realized. Probably in the S3 backend, there is some caching happening. So after running some experiments one after each other in the S3 setup, we saw quite some acceleration. Which is not good if you're trying to calculate a cold start performance. So if you want to give it a go and check out some benchmarkings, make sure that you add a cooldown period between cloud tests. Yeah, and some exciting news that's coming up and that's already here. So we have a new version, 0.13. It has full AWS S3 native authentication. Now we also support GCS, and we have some usability improvements. And in the roadmap, we have some very cool stuff coming up. We are going to support sharded models. We are going to optimize multi-GPU model loading. We are going to have parallel multi-file loading, and we are also planning to support GPU direct storage. And we are especially excited about the GCS support. We are working with the GKE team, and the first impressions from the GKE team is amazing. They see 96% model load time reduction with the model streamer when used with VLLM in compared to downloading the model from the cloud object storage directly, which makes us happy. Yeah, so here are some QR codes for you. The first one is to the GitHub repo, and this is a QR code for the benchmarking white paper. We have a lot of results if you want to have a look. And if you have any questions, we are going to be at the booth after this talk. We are very happy to answer any questions, chat about how you experience this challenge. And one more thing, we are very excited about this specific KubeCon because the core of the Run AI platform, our Run AI scheduler, is now available under Apache license. So if you are scheduling AI workloads, we are very happy to hear your feedback. Any feedback, any contribution, any early adopters are very much welcome. And you can also come to booth if you want to talk about the scheduler. We are very happy to hear your ideas and opinions.
And we call it Kai Scheduler, okay?
Yes.
Kai Scheduler.
Yes, whatever you call it, Kai, KAI. Yes,
Good.
that's it for today from us.